Okay, welcome back. Looking at the actual mathematics involved with calculating rate and predicting rate depending upon the circumstance. So the topics that I'm going to go over is really taking a look at rate three different ways. Now, there's a lot of different ways to calculate rate. So at the AP level, we would teach you something called integral rate, where we're taking a look at the line tangent to the curve. So a little bit of pre-calculus and calculus mixed in there, but pretty basic stuff. You don't actually have to do calculus. You just have to understand a tiny bit of it. But we're not going to do it at this level because it's not required. What we're going to do is take a look at rate in terms of how it relates to the balanced equation. And then we'll take a look at how rate is related to the lab data that we would get based upon what's called differential rate. And then in the next video, I'm going to take a look at reaction mechanisms and getting the rate expression from that and from the what's called the molecularity of the rate determining step. All right, so a reaction rate varies directly as the product of the concentration of reactants. Now, that would be what we call a rate equation or rate expression. Most commonly at the AP level, they call it a rate law. And there's a lot of different ways to quantify the rate of a reaction, but the easiest thing to control of the five factors would be the concentration of the reactants that you're putting into the reaction vessel. So we're going to start with that one. Okay. All rate laws, all rate expressions are in the form rate equals K, which is the rate constant, and times the concentration of reactants. Remember, I said the brackets represents the concentration of, and then we're going to raise it to some power, which is known as the order of the reaction. Before I go through that and break it down, do understand that all of these rate equations have to be determined experimentally. And like I said, if it was a normal school year, we would do that in the lab. So I'm going to provide some lab data for you, and then we'll take a look at it that way. Before we get to it, talk a little bit about the rate constant. Since we're controlling the concentration of the reactants, when we say K, lowercase k for the rate constant takes care of all the other four factors: the presence of a catalyst, surface area, etc., temperature, and so all of those things are bundled into the rate constant, and so therefore we know, for instance, a change in temperature changes the speed. So therefore, there's only 1 K for each given temperature. So if you change the temperature, you also change the value of K. If you add a catalyst, you change the value of K. So do understand, again, we're going to go with this at this level, that there's only 1 K for each reaction, but there's a different K for that reaction at every single given possible temperature. So, essentially there's an infinite number of K values for a reaction. The exponent of that expression is called the order of the reaction, and that has to do with the mathematics of the reaction. If you see an exponent of 1, that means it's a first order reaction. Now that means something in terms of molecularity, which we're going to talk about in the next video. In other words, it's not the number of particles that you have like when we're doing stoichiometry. It's also, in terms of the collisions, the type of collisions that are going on, and we'll get into that in the next video. But if something is first order with respect to a chemical, that means that if you double that chemical, you also double the speed. There's a 1-to-1 ratio there between speed and concentration. So if you triple the concentration, you triple the speed. If you quadruple the concentration, you quadruple the speed. If you dodecaduple the concentration, you increase the speed by a factor of 12 times faster. If it's a second order, if you have an exponent of 2, you have a squared relationship. So doubling the concentration squares the rate. So it increases by a factor of 4, 2 squared. If you triple the concentration, now you're looking at 3 squared, 9 times faster. Dodecaduple, you're looking at 12 squared, 144 times faster. So the exponent right now, in terms of this video, when we're doing the mathematics, represents that that algebraic relationship. However, in the next video, we'll take a look at it. It really determines the nature of the collisions themselves. All right, so before we get to this data, let's break this down a little bit further. All right, so I said that these equations could be called rate expressions, rate equation, or rate law, depending upon who writes the equation. Usually in AP Chem, they call it the rate law. If you have a reaction, let's say we have 3A plus 2B produces A3B2. Now, again, it's not the number of collisions that determines the rate law. It's the type of collisions, and I said we'll get into that in the next video. So very possibly for a certain reaction, you could have a rate law like rate is equal to K times, let's do A times B. Now notice, you would expect that the exponent would be related to the number of moles, but it's not. We're raising A to the first power even though we have 3 moles of A. And we're raising B to the first power even though there's 2 moles of B. It depends upon the type of collisions. Now, if we were to do this with a different reaction, let's say, A and B, I'm just using generic letters, but we could throw in chemicals there. Let's say we change the chemicals and we have some sort of organic material for A and some sort of solvent to do solvolysis with in B. Then maybe we run the data and we find out that, hey, for this particular different reaction, we got second order with respect to A, and B had no effect on it at all, what they call a zero order reaction. We can very easily get this as a rate law, K times A squared. Again, the rate law is based upon the data that you get from that lab and not from the stoichiometric equation that's put before you. They love to throw in the balanced equation to fool you. Balanced equations are a relationship that's based on thermodynamics. Remember, we said in the first video, thermodynamics, how much product we get. Rate equations are based upon the kinetics, which is based upon the type of collisions that you get, the type of materials, the temperature, all of that stuff. So thermodynamics is different than kinetics. So we can't look at a thermodynamic equation like that and then base our rate law. Like if you were to write, for instance, you look at that equation and you write rate is equal to K times A cubed times B squared. Well, that is possible, but you would still have to run the lab data to support it, and chances are it's not, because when you have a third order reaction, those collisions are very rare, and again, we'll get into that in the next video. So let's get rid of that. Now, what good is the stoichiometric equation then? Well, we can base rate on stoichiometric equation from a conceptual point of view. Think about it. If you are using chemical A and you are using chemical B to produce this product, right, triammonium dibiide, we need 3 particles of A, 2 particles of B to produce only 1 particle of product. So that means that we are consuming A 3 times faster than we are producing triammonium dibiide. Not only that, but the change is going 3 times faster and in the opposite direction. So if we were to find rate law in terms of A, we would get a different value than if we define it in terms of B. A is disappearing 3 times faster than the product is being made. B is disappearing 2 times faster than the product is being made, and that's only because of the number of particles that are needed to create the product. And the change in A and the change in B, A is disappearing, B is disappearing, yet triammonium dibiide is appearing. So we would use usually a positive symbol for the direction of the change for the product, and negative symbols for the direction of the change for the reactants. So we don't really want 3 different numbers for our reaction rate. We said we could define reaction rates in terms of how fast products are appearing or how quickly the reactants are disappearing. So in order to get the same value, we would have to do this. All right, in order to get our rate, we'd have to say, if we're going to do it based upon the change of A is disappearing, so we're going to put a negative in front of it, and it's changing 3 times faster, so whatever the time is, t in time, it's going to be 3 times faster. than B, or I'm sorry, than our product. Now, that rate number would also be equal to a change in B if we took the time for the change and we put a 2 in front of it. And then we could say, well, that's equal to the change in the appearance of our product over time. Because that's what rate is, right? Change over time. So how would this number work out? Well, let's say, for instance, it took 1 second for the change to occur, and we had a change of producing 1 mole of product, so our per liter. So our product rate would be 1 mole per liter second. So what would we have to do to B in order to make it come out to be 1 mole per liter second? We're changing twice as much B, so that's 2 moles per liter seconds. But if we take the time and multiply it by 2, then we get 2 moles over 2 liter seconds. The 2 cancels out, and we're left with 1 mole per liter second, just like we did for our product. Same thing here with A. We would have 3 moles of A that would disappear. Sorry, put the negative in front, it's disappearing, per liter second. So we would have to take the time here and put a 3 in front of it in order to get the 3's to cancel out. So again, our rate winds up being 1 mole per liter second, regardless of what we use to base that rate on. Now that's a hard concept. AP kids struggle with that concept a little bit. Here's another concept they struggle with. Why would this be true? That's a true statement. And it's a true statement because now we're looking at the reverse process. Remember, at equilibrium, the reverse process and the forward process are occurring at the same speed. So if we put the negative in front of one and the positive symbol in front of the other, we're just saying that they're changing in the opposite direction. We're not saying that one's going forward necessarily and one's going in reverse direction, because we're at equilibrium. Both things are happening. We're just saying that one is changing in the opposite direction of the other. So expect some multiple choice questions on that sort of topic. And again, they love to fool you with this last one because people think it's not true, but it is true. The negative doesn't have to go in front of the thing that is disappearing. All right. Second, they give you a general question like this. Let's say we have a reaction and they give you the balanced equation. A plus 2B produces A dibiide, if there was such a thing. Reaction second order with respect to the concentration of A. By what factor would the rate increase if we double the concentration of the reactants? Okay, so here's how you do it. I always do a baseline first. Let's get our rate law. It says it's second order with respect to A. And they didn't mention anything about B. That's okay. That would be 0 order with respect to B, and anything raised to the 0 power gives you a value of 1. So it doesn't change the value of the rate by having it in there. In other words, we're saying that B has no effect on the speed of the reaction. And again, in the next video, I'll explain 0 order reactions and how that's possible. So we can just write our rate law. Rate is equal to K times A squared. Now, K is a constant, and we can make up any value for this. We don't need to know it. So I'm going to start with my baseline. So it doesn't matter. If this was 5, and let's say our original concentration of A was 2, then our rate would be 20 moles per liter second. So if we doubled the concentration of A, we would get 5 times 4 squared, which is 80. Either way, the reaction is going to run 4 times faster. We do 80 over 20, that's a factor of 4. It's going to be 4 times faster. So you don't get whole numbers usually in these problems. I'm going to do a couple examples where you do, but normally the value of the rates are going to be things like 1.3 times 10 to the minus 6 moles per liter second. So they're not things that are easy to calculate just by using your head. Using your head. I mean, not easy to calculate in your head without, kind of working it out. So I always say, look, it doesn't matter what the rate constant is, so let's choose the easiest number possible to substitute in here. So I'm going to put in a 1. That's easy to multiply by. And as far as our baseline, it doesn't matter what value I pick for A, I should still get 4 times faster. So I'm going to pick 1 again for my value of A, and square it, and I get a baseline of 1. So now they're saying let's double the reactants. Again, we don't care about doubling B. It has no effect on it. So my comparison, so this is my initial baseline, and then this is my prediction. Rate constant stays the same, but now we're doubling the amount of A. We get 2 squared, and that's 4. And again, we get 4 over 1. So this is going to be 4 times faster. Please try this problem. Give you a chance to work it out, and then I will come back and go over it. I'll pause. I'm done pausing. Here we go. All right. So that this is second order with respect to A, first order with respect to B. It doesn't matter what the balanced equation is, because based on that description, the rate has to be K times second order with respect to A, so A squared, first order with respect to B, so A squared B. How much faster would the reaction run if we triple A and double B? So again, I'm going to start with my initial baseline. 1 times 1 squared times 1. See how easy that is? Equals 1. And then my prediction is going to be K, which stays at 1. I am going to triple the amount of A, so 3 squared. And I am going to double the amount of B. So I get 1 times 9 times 2, I get 18. So this is going to be 18 times faster. All right, easy. Put a whole bunch of those on the test, right? All right. Second way to do this is to use what's called differential rate law or differential rate data. So they will give you a set of data like this. And it's funny, the questions for Chem Honors are the same as for AP Chem. And the typical differential rate law problem is they give you data, and then they say, all right, well, based upon that data, what's the rate law? What is the value of the rate constant based on that data? And if we were to substitute in new data for, or try a new experiment using different concentrations for A and B, what is the actual rate of that reaction? Can we predict it? And the answer is yes. Here's how you do it. In order to figure out how the change in the concentration of A affects things, we have to find data trials where A is changing, but we have to keep B held constant. If B and A change at the same time as we go from one experiment to another, we can't assign cause and effect. And you learned that in other science classes, right? We're changing one variable at a time. So if I look at trials 1 and 2, B is held constant, but A is changing. So I'm going to use those trials. So I'm going to concentrate on trials 1 and 2. Now, there is a little formula for this. If you look at this, we are keeping B held constant, but we are doubling from trial 1 to 2 the amount of chemical A. And as a result, it runs approximately 8 times faster. So 2 raised to the x equals 8 is actually third order. 2 cubed equals 8. But, like I said, there is a formula for this, because the numbers that we're going to use on the test won't be this simple. I keep this simple because I'm a teacher. We get confused easily. All right, so what we're going to do is we're going to set up A, and we're going to do the concentration of A at the high concentration over concentration of A at the lower. And we're going to raise that to the power of x. And then we're going to do our rate associated with the high concentration over the rate for the low concentration. So when I do that, I get 4.0 moles per liter. I like to write the units out. 2.0 moles per liter for the lower concentration. And we're going to raise that to the power of x. Our rates are high rate, 16.15 moles per liter seconds, over 2.02 moles per liter seconds. Now at this level, your values are always going to come out to be whole numbers, because you're only required to do algebra 1 here. So this is 2 to the x is equal to 8. Therefore, x is equal to 3, which means 2 cubed equals 8. So this 3 represents the order of the reaction. We would say that this reaction is third order. Let's write that. Third order with respect to the concentration of A. All right, so we have part of our equation. Now we just have to go back and do the same thing for chemical B. How does B affect this? Well, we're going to have to find two data trials here where A is held constant, first and third trial, but B is changing from 2 molar to 6 molar. And again, sometimes you can just look at the numbers. We're tripling the amount of chemical A. We're going from 54 down to 2, or 2 up to 54 rather. So we're looking at 3 to the X is equal to 27. Again, this is another third order relationship. So I'm going to write that out. We already wrote the equation once. I like to keep track of which trials I'm doing. I want to do a change in B, but in trials where A is held constant, so I'm going to use the data from trials 1 and 3. And we said that data was 6/2. 6.0 moles per liter over 2. Yeah, we're doing the same thing by analogy here. 54.57 moles per liter seconds over, was it 2.02? Yes. 2.02 moles per liter seconds, and this comes out to be 3 to the X is equal to 27. Therefore, X is equal to 3. We would say that this is third order with respect to the concentration of B. Now, another question that they might ask you before they ask you for rate law is they might say, well, all right, what is the overall order? To get the overall order, you add the two orders together. So overall order of this reaction would be 3 plus 3, which is 6th order. Our rate law is equal to K. Why did I write rate law? I should have just wrote rate. Rate is equal to K times A cubed B cubed. Okay, great. So that answers part of the problem. They wanted to know what was the rate law. Third order respect to A, third order respect to B, and we just stick in our rate constant. Now they want to know the value of the rate constant. Okay. Well, look, sometimes I don't plan well. Let's move this out of the way. Let's move this out of the way. That was the next question. Okay, so in order to get the value of K, two things. One, let's solve this for K. K is equal to rate over A cubed B cubed, right? Little simple algebra. And now, since the rate constant is a constant, it doesn't matter which data you use as long as you have a rate, a value for B, and a value for A, and you take it from the same trial. So I'm going to take it from trial number 1, where we have 2 molar for each concentration and 2.02 for the rate. So I'm going to substitute that in. 2.02 moles per liter seconds over 2.0 moles per liter cubed for A, 2.0 moles per liter cubed for B. And this comes out to 2.02 divided by 2 cubed times 2 cubed, which is 64, and we get 0.032. Now the units mess people up. You got to handle the units like you would fractions. So we have moles over liter seconds in the numerator, and then we have moles to the 6th over liters to the 6th in the denominator. So dividing by a fraction is the same as multiplying by its reciprocal. So we would do liters to the 6th over moles to the 6th, and our unit comes out to be, when we cancel things out, we get liters to the 5th over moles to the 5th seconds. Now, at the AP level, you do this problem, they want to get 50% credit just for the units, 50% credit for the number, 50% credit for the units. For some reason, people struggle with the units. It's fractions. I like fractions. They're my friends, but not everybody does. A shortcut is, if you know the overall order, flip the moles and the liters, and then just subtract 1 from the overall order. So this was 6th order overall, so we're going to do, instead of moles over liters, we'll do liters over moles, and we'll make it to the 5th, 1 less. That works. And then now they want us to go back and substitute in data for the last part of it. So that now that we know the rate, we know K, And now we can substitute in what were the values they wanted. They wanted 3.2 and 5.3 molar. All right, so let's do that real quick. Most common mistake I see students make is they'll write cubed, but then they'll forget to actually cube the value. 5.3 cubed, and we get 196.99, so that would be 200, and that makes me think I put in the wrong value. So let me see, because that 3.2, 5.3, no, that's correct. All right, so let me just check my math here, because my editing skills are poor. All right, rate constant is correct, 0.032 times 3.2 cubed times 5.3 cubed. That's it. Yeah, there we go. I must have hit the wrong button somewhere on the calculator. I got 156, which is familiar. You got to figure I've done these problems for 20 years, the same problems over and over again. All right, so we get a rate of 156 moles per liter seconds. Let's try another one. Move this guy up. We'll move this guy up. Oop, let's move this guy down for symmetry. All right, we're not getting much symmetry there. Things happen. All right, so say they give you this data. Now, if you've already caught on to how to do this, just go ahead and do it. I'm going to go through this a little faster. Pardon me. Again, if I'm trying to figure out, first of all, the rate law, then I'm going to take a look at how A is changing, but B is held constant. So again, coincidentally, trials 1 and 2. So when I do trials 1 and 2, I already wrote the equation on the last slide, so I'm not going to duplicate it here. We're going to do rate high for A over rate low, raised to the X is equal to rate high over rate low, and that gives me 4 to the X is equal to 16, so X is equal to 2. This is 4 squared equals 16, so this is second order with respect to A. And now we'll do the same thing by analogy with B. Now, which data trials? Let's go ahead and select them. All right, A is held constant in trial 1 and in trial 3. So we're going to use the data for B from those trials. So 6 molar over 3 molar. Again, raised to the X. High rate over low rate. Oh my goodness, they're the same. I must have selected this for a reason. I did. In other words, doubling the amount of chemical B had no effect on the reaction. So we get 2 to the X is equal to 1. So X must be equal to 0. This is 0 order. No effect. 0 order with respect to B. To the concentration of B. So if they ask you for the overall order, you would get 2 plus 0. The overall order is 2. Okay. So we write the rate law. Rate equals K times A squared, and that's it. Nothing for chemical B. So let's solve to get our rate constant. K is equal to rate over A squared. Now I can choose the data from any of these trials. I like that the concentration of A is 1 molar. So I'm going to choose trial number 1 for my data. So the rate is 4.02 moles per liter seconds. And we're going to put that over 1.0 moles per liter. Again, remember I said you flip the liters and the moles and subtract 1. So if we work out the, we've got to square this. If we work out the fractions, we get 4.02 liters per mole second. Take the overall order, subtract 1, flip the moles and the liters. All right, so there's our value of K. And then lastly, they want us to substitute in some new values. So rate equals 4.02 times A squared, 2.4 moles per liter squared, but we don't care about B being 3.3 molar because B has no effect on the reaction. So 2.4 squared times 4.02, I get a rate of 23.1552, so 23 moles per liter seconds. Alright, so this is already a very long video, so I'm going to go right to our last one that I want you to try on your own. Let's see if we can get all that fit in without the answer being there. Okay, there you go. And I'll pause while you work that out. Okay, I'm back. Alright, so you could check your work. Again, B is held constant in trials 1 and 3. A is held constant in trials 2 and 3. So I do concentration high over concentration low, raised to the x is equal to rate high over rate low. Substitute in. Your work should look the same, right? And we are first order with respect to A, second order with respect to B, third order overall. So our rate law is K times A times B squared. We solve for K. Substitute in any of the sets of data, trial 1, trial 2, or trial 3, and we'll get 0.016 liters squared over mole squared seconds. And then we substitute in what they asked us to for A and for B. And we just have to make sure that we square B. Did I do that? Then check 4 times 1.38 times 0.016, and I get, yeah, 0.088 moles per liter seconds. That's differential rate law. Next video, reaction mechanisms and molecularity.